So we've collected two examples. Well, one example, the integers, and then another example, which is just, it's a family of examples. You take your favorite field, you look at polynomials over that field, and that is also a PID. So we have sort of one sort of isolated example, the integers, and then a family of examples, an example for any field. In this next theorem, we are going to show that GCDs always exist in PIDs. So whenever you have a PID, you will get GCDs. And the theorem is exactly this. So let R be a PID. And X, Y, and R be not both 0. Just like, when we were doing GCDs with the integers, we don't want to look at the GCD of 0 and 0 because it doesn't exist. Let's set I to be the ideal generated by X and Y, which is the collection of all xm plus yn, where m and n are in R. Then, well, I is an ideal in a PID, so I is equal to D for some D in R. So I is principally generated because R is a PID. And this D is a GCD of X and Y. In particular, there exist Bezout coefficients S and T in R such that XS plus YT is D. Okay, so this is sort of all of that work we did with Z and finding Bezout coefficients. It all comes from the fact that Z is a PID, and that comes from the division algorithm. So again, once you have a division algorithm, you sort of get all of the things we've been using. All right, so let's go over the proof of this. So proof. Well, what needs to be proved? It needs to be proved that the D that we get here is a GCD, because I is obviously an ideal. We've dealt with those before. And then there needs to be a comment that where this comes from. So we just need to show that D is a D is a GCD. All right, so we know that the ideal generated by X and Y is the same as the ideal generated by D. This tells us that X and Y are in the ideal generated by D because X and Y are in the ideal generated by X and Y. So there exists some M and N in R such that MD is X. Sorry, let's do it in the opposite order. X is MD and Y is ND. That is, D is actually a common divisor of X and Y. Awesome. Okay, that's the common divisor part. Now we have to do the greatest part. So let's suppose that E in R is such that E divides X and E divides Y, which is to say there exists some, I don't know, M1, M prime, N prime in R such that X is EM prime and Y is EN prime. Okay. All right. Let me also note there's one intermediate step here. I actually want to go in and argue this this Bezout coefficients first. Let's keep that. Let's keep this in our pocket for a second. So we'll go back. Let me highlight this. We'll go back and use it. Also, since D is in D, the ideal generated by D, and that's the ideal generated by X and Y, there exists some S and T in R such that D is XS plus TY. And those are our Bezier coefficients. And now that we have these Bezier coefficients, we're going to go ahead and plug in what X and Y are. So we're going to plug in the highlighted area. Okay, so we plug that in, and what do we have? Well, there's an E in both of these terms, so we can factor it out. And what does that tell us? It tells us that E divides D. And that's what we wanted to show. So, D is a GCD of X and Y. And we also have our Bezier coefficients. So just to be clear, these are the Bezier coefficients. All right, so in the GCDs don't exist in general, but in the realm of PIDs, they do always exist. And again, this theorem is prescriptive. It tells you how to find the GCD. You look at the ideal generated by X and Y, and you look for a principal generator. If you have a division algorithm, you can find that principal generator is somehow a minimal element in the ideal. Again, these don't exist in general, but in this setting that they do.